Okay, so if there is a solution that those A's are not all zero, then that means you can find a K's within those within these vectors and write it this way, which is the linear combination of the remaining vectors. Okay, and in order to do it that way, this AK cannot be zero, and that's why like we have to have a solution that is not zero first. Okay. And you may ask like, would it be possible that okay now the AK is non-zero, but the rest A are zero? Would that be possible? Meaning that okay, this is the put it more direct way is like okay, they are all zero, but only the K item is, for example, like 1. Such like, would it be possible that the solution look like this one? Just an example, like the answer is no, no. Because if that is the case, then you will figure you will find that like you will get something like this one equals to 0. Of course, like this cannot be 0. Otherwise, the discussion is kind of meaningless. Okay. Right. That's just a small exercise here. Okay, then is the span, which is related to the graphic expressions of like how vectors, how you add up vectors and how you multiply vectors. Okay, so first we go through the definition. Spans. Okay, so let's say that we have a collections of vectors v1 to vn here, and what is the span of such collections or such sets small v here? Okay, so the span of it is the collections of all the linear combinations out of from those vectors. Okay. Yep. And of course, like you can put all 0 there, so actually it's you will get the 0 vectors as well in that span, and actually it's the subspace as well. It satisfies the subspace. So how does it look like when you think of like graphic expressions? put it here. Okay, so the span, let's say that we have like these two vectors here, v1 and v2, and you want to know the span of it. So this is the linear combination of these two vectors, right? And you start to construct the whole span, like the whole space, like spans bound by these two vectors. You can start from like 0. Okay, so if that is 0, then you will get 0 here. That's for sure. And you may think of like 1. Okay, so if that is 1, then as we just show it, you will get these vectors as well. And then you start to think about, okay, how about half of it, like 0.5. 0.5 here. Okay, so not only this point, you also get this point as well. So actually you can get all the point here along this line and also the extension of it. Okay. And you change the number of A as well. For example, like 0.8. Let's say that 0.8 V1 and V2. So that will like this one. Okay, so if you continue to do it, you will figure it out like, okay, so actually it's the whole plane. You can do it, for example, like if you want to get something here, what is the A1, A2 look like? It has to be negative. Like you will figure out some like negative number will help you to achieve this point as well. Right? You can continue to do it and until you construct the whole plane there. So when we talk about spans, it's like we have the ingredient, like the basic ingredient, which is the vectors, and then we try to expand it on the plane or like on some space. Okay. Now we are going to cover the concept of basis, which is kind of the other way around. It's like I already know the whole what's the whole space look like, and what ingredient I need to construct it. Okay, so it's the other way around. Okay, so this is the definitions. Okay, so let V be a vector space and a set of vectors, which is denoted as small v here, is called the basis of the vector space, big B, if it satisfies the following two conditions. First is that this vectors has to be linearly independent. Okay, and the span of this small v, or like the span of this vectors, has to be the big B over there. So you can think of that as the minimum set of vectors you need to explain to express every vectors in the big V there as a linear combination. Okay, and of course, like the candidate of basis is not unique. You can think of a lot of possible here. Okay, so let me quickly use example. Okay, so as we already showed that this V1 and V2 can span the whole plane here, or like you can think the board, right? And what if we add one more vectors here? We call it W, W1. And W1. Okay, so does it help you to construct the whole plane? Actually, no, because as you can see that these vectors is actually